In this section, we want to look at rational exponents. But I want you to notice, before we start talking about rational exponents, I have listed out some bases and what their value is raised to various powers. You can use this, it'll save you some time, that way you may not necessarily have to use a calculator, but you can keep this paper for handy reference, especially as we go through the process of working with rational exponents. So I would highly recommend that you keep this note page handy for yourself. And we're going to begin talking about rational exponents. Now remember, a rational number is just a number that can be written in fractional form. So a rational exponent, an exponent represents the number of times the base is used as a factor, but a rational exponent is a fractional exponent. That's a C. And if we have b to the 1/2, I can rewrite that as the square root of b. If you've worked through ALEX, you might have seen this already. So 27 to the 1/2 is the square root of 27. If we take 36 to the 1/2, that's the square root of 36, and we know what that is. That just happens to be 6. If we have 6 times x to the 1/2, notice only the x is raised to the 1/2 power. So this becomes 6 to the square root of x. Now let's think about it going the other way. If I have the square root of 32, I could rewrite that with a fractional exponent or a rational exponent, and it becomes 32 to the 1/2. If I want to write 2 times the square root of x with an exponent instead of the square root, it becomes 2 times x to the 1/2, because that is the square root of x. Now let's look at it just thinking not necessarily about square roots. If we look at the next thing I have written down, it says if 2 cubed is equal to 8, then 2 is a cube root of 8. So here we're talking about an nth root. If a to the n is equal to b, then we could say that the nth root of b is equal to a. So if we wanted to say that, if we know that 2 to the 4th equals 16, we know that that's true. 2 to the 4th does equal to 16. We can say that 2 is a 4th root of 16. Now here on these next problems, you might want to refer back to the first page that we started with. Here I have the cube root of 125, and I want to simplify this, the cube root of 125. Well, we know that 125 is 5 times 5 times 5. So if I take the cube root of 125, we simply get 5. If we take the 5th root of 32, what number to the 5th power is equal to 32? Well, hopefully we remember that 32 can be rewritten as 2 times 2 times 2 times 2 times 2, and 2 to the 5th, in other words. So the 5th root of 32 is actually 2. If I want the cube root of 1,000, well, this is the same as saying the cube root. We know that 1,000 is 10 times 10 times 10. So the cube root of 1,000 is 10. Notice we got 3 zeros, so that tells us that the cube root of 1,000 is 10. Now, we can rewrite a rational exponent as a root. In other words, b to the 1 over n is equal to the nth root of b. Whatever's in the denominator is the number of the root. So 8 to the 1/3 I could rewrite as the cube root of 8. And we want to know, okay, so what number times itself 3 times gives us 8? And hopefully we remember that 2 times itself 3 times is equal to 8. So 2 is the cube root of 8. I could rewrite 27 to the 1/3 power as the cube root of 27. And if you look at your sheet that I had given you at the start, you can see that 3 cubed is 27, so 3 is the cube root of 27. (256 to the 1/4 means I want to take the 4th root of 256. Now, if we look at that sheet that I gave us a minute ago, I'll pull it back up. Notice if I just go across to the 4th roots, I'm looking at this line. We said the 4th root of 256, well, here's the one we're looking for. So I'm going to go back over. The 4th root of 256 is 4. If we look for the 4th root of 2,401, you can go back and look at that sheet one more time, and if you look along the powers to the 4th, we see that 2,401 is equal to 7 to the 4th, so 7 is the 4th root of 2,401. Okay, now this one's a little bit different. Notice we have b raised to the m over n power. Remember we said that what's in the denominator is the nth root, but notice this time I can rewrite as the nth root of b raised to the m power. Generally we'll want to take the root first and then raise it to the power. So if we look at 8 to the 2/3, I can rewrite that as the cube root of 8 squared. And we've already seen that the cube root of 8 is 2, so if I have 2 squared, this is equal to 4. Kind of work our way from the inside out. Again, several of these you should be beginning to recognize, but you may keep this note that I made for you available so that you have those powers written out to the 5th or 6th power. Right, so if we look at 27 to the 2/3, we're going to take the cube root of 27, and then we're going to square that. So the cube root of 27 is 3, and if we square that, we get 9. Hopefully you find that these are a lot easier to work with maybe than they look like at first glance. If I take 32 to the 2/5, that means I'm going to take the 5th root of 32, and then we're going to square that. So the 5th root of 32 is 2, and 2 squared is 4. Try the next one. I'll give you a few seconds. Go ahead and try the next one. Okay, if we look at 81 to the 5/2, that means we're going to take the square root of 81, and there's no need to put a 2 there. If there's no number right here, a 2 is understood. Okay, let me go ahead and erase that. So we're going to take the square root of 81 and raise that to the 5th power. Now the square root of 81 is 9. And 9 raised to the 5th power, you could either use a calculator or you can look at the sheet that I gave you and you see that 9 to the 5th power is 59,049. The last thing we want to look at in this section is how to solve an exponential equation. And an exponential equation is an equation that has the variable in the exponent. The variable is in the exponent. That is an exponential equation. If you were to model an exponential equation on the graph, you would see that generally it starts out growing very slowly, but over time it begins to grow more and more rapidly. For instance, an exponential equation would look something like this: slow growth, and then all of a sudden it takes off. If you've been watching the news at all, they say that the coronavirus follows an exponential curve. It starts off rather slowly, and then all of a sudden it picks up speed and escalates. Financial applications use exponential functions. So you're going to continue to see exponential functions. But today, we just want to see how to solve an exponential equation. We're not going to worry about the graph right now. And we're going to see that it's really not too difficult. Here's an example. If 5 to the x equals 5 to the 3, notice the bases are the same. If the bases are the same, then the exponents are equal to each other, and we get that x equals 3. The next one, notice I have the same base. If 4 to the n equals 4 to the 1/2, then n is 1/2. If the bases are the same, then we can set the exponents equal to each other. Now, obviously, you're not always going to have problems where the bases are the same, but we may be able to make them the same. For instance, here I have 5 to the x equals 125. Our goal is to rewrite the number, the larger number that doesn't have the exponent, with the same base, or see if we can get both sides to have the same base. So here we have 5 to the x. And hopefully, if you're looking at your sheet, you see that 125 is 5 cubed. Really, I hope maybe you already know that. So x is equal to 3. If we look at the next one, 9 to the x. Well, if you look at your sheet, is there a number whose base is 9? Or is there any way that we can raise 9 to a power and get 729? And if you look to your sheet, you can see that yes, 729 is equal to 9 cubed. So here again, x is 3. On this next one, we have 12 to the 2x plus 3 equals 144. Well, 144 is 12 squared. So we have 12 to the 2x plus 3. If the bases are the same, then we can set our exponents equal to each other, and we have an equation that we can easily solve. And we get that subtract 3 from both sides. We get 2x equals -1, divide by 2, and we get x equals -1/2. let's do one more. 16 to the 2x minus 1 equals 8. Now, I cannot rewrite 16 with the base of 8, and I can't rewrite 8 with the base of 16, but they both can be rewritten with base 2. We can rewrite 16 as 2 to the 4th times 2x minus 1, and this is 2 cubed. So using our rules for exponents, we know that this becomes 2 to the 8x minus 4 equals 2 cubed. Now I have the same base, so I can set my exponents equal to each other. 8x minus 4 equals 3. Add 4 to both sides. And 8x equals 7. Divide by 8. And x equals 7 over 8. Okay, maybe we better do one more that's similar to that. If I have 4 to the x minus 3 equals 128. Now, if you look at your chart, you don't have anything 4 raised to any power that equals 128. So let's think about if our base was 2. If we multiply, we have 2 to the 6th is 64. So if we multiplied that by 2, we would get 128. So we can say that that's 2 to the 7th. Right? If I rewrite 4, it's going to be 2 squared raised to the x minus 3. And now we have to multiply the x minus 3 times 2, so we get 2x minus 6 equals 2 to the 7th. And we can set, because our bases are the same, we can set our exponents equal to each other. Add 6 to both sides, and we get 2x equals 13. And x, if we divide both sides by 2, x is 13 halves, or we could say that it's 6 1/2. Either answer would be correct, either 13 halves or 6.5. Okay, I'm going to go ahead and give you some practice. This is assignment number 4 for this quarter. Remember, you can keep your notes. You can use your notes on a quiz or a test. Page 410. 18 to 50 even. And 60 to 66 even. Okay, my plan is to have a test over 7.1 through 7.4 the Wednesday before we leave for Easter break.